Just a minute, Jyoti. I think,
Yes.
what do you call her? Sir, I think, is not able to hear us. Just let it sort out this problem. Sir, are you able to hear us? Sir. Jyoti, just a minute. I called to sir. Just a minute. Just
Okay, ma'am.
Jyoti, sir is going to log out and log in back again. Let us check first the audio of sir. Then
Okay,
we will
ma'am.
start. Huh? Just
Okay,
a
ma'am.
second. Sir, can we check the audio, sir, once? Sir, can we check the audio? Am I audible? Hargopal, sir. Hargopal, sir, am I audible? Sir, am I audible, sir? Yes, Dr. K. Ranjam. I know I'm audible to you, but I'm not audible to sir. I'm not audible to sir. There is some problem with sir's microphone. Thank you for your response, Dr. Murli. Hargopal, sir, am I audible? Dear participants, there is some problem with Professor Hargopal sir's microphone. Have little bit of patience. He's again, going to join in, log in back. So am I audible now? Hargopal sir, am I audible now? Sir, am I audible? So you're not audible. You're not audible. You're not audible. So you're not audible, sir. So you're not audible. You're not audible, sir. So do you want any kind of a help? Dr. Lalita, you would like to speak to sir to check the sound there? So, sir, am I audible now?
Yes.
Just a minute, Dr. Murli. There is some, microphone problem of the speaker.
Madam, am I audible now?
Yes, sir. Yes, sir. Now you're audible.
Right. Thank you.
Now you're audible, sir. Yes.
Yeah, I'm sorry.
Dr. Jyoti?
Yeah.
No problem, sir. It happens.
Yeah.
It happens. Sometimes, we cannot trust the laptop and technical things. Dr. Jyoti, please start the session.
Yes, ma'am. And sorry to participants for inconvenient cause due to the technical issues. Good morning, all. I welcome you to the 6th day of 10th day online faculty development program sponsored by ICSSR. It gives me immense pleasure to introduce today's resource person, Professor Haragopal sir. Sir is currently working as director, Asian Algo Private Limited, Hyderabad. Sir has served a head department of statistics until his retirement and has a rich teaching experience of 37 years in Usmania University. He has held various administrative positions to name a few. Sir has served former professor, Department of Mathematics, BITS Pilani, Hyderabad campus, principal consultant, data science practices, Envision Enterprise Solutions Private Limited, retired professor and former head Department of Statistics, Usmania University, and sir has served 3 terms chairman Board of Studies in Statistics. Under sir's guidance, 25 PhD, 7 MPhil dissertations supervised in various subjects. Professor Haragopal sir has immensely contributed in the research through 125 research papers published in national and international journals. Sir has rendered his services as a member to name a few, consultant and institutional review board member for Aurobindo Pharma, Hyderabad, consultant cum mentor to SPSS Inc., former president and life member, AP Society for Mathematical Sciences and ISPS, life member, AP Academy of Sciences, life member, Society for Development of Statistics, life member, India Society for Probability and Statistics. Sir has memberships in editorial boards of journals, to name a few, editor for International Journal of Agricultural and Statistical Sciences, editor for Statistic 1 Descriptive Statistics and Distributions, Telugu Academy, Farmer Associate Editor for Assam Statistical Review, Dibrugarh University, Assam. Sir has involved in surveys and data analysis undertaken by various states, to name a few, involved in the habitation survey conducted by Government of AP, involved in poll analysis of Karnataka state, involved in data analyzed for the BC surveys handled by ISI Hyderabad, and done many market research and government projects, data analysis, involved in analyzing the data in intermediate marks weightage in MSET by Government of AP. Sir has delivered uninvited talks in 99th Indian Science Congress during January in the year 2012 at KIIT Bhubaneswar, Orissa. Sir has delivered many invited talks and resource persons to many state and central universities and research institutes across the India. Once again, I welcome to you, sir, to the session.
Yeah, sure. So can I share my...
Gopal, sir, good morning. Sir, good morning and welcome you to today's program. It's a privilege to Reddy Women's College to have you for this 10-day FDP program. Thank you for accepting our invite, sir.
Sure. So I'll share my screen. Yeah.
Yes, sir.
Yeah.
Visible, sir. Your screen is visible.
Yeah. Is it visible? No.
Yes, sir. It's visible.
Yeah.
Simple, multiple stepwise and logistic regression.
Yeah. Correct. Yeah. So, before going to this particular presentation, I just wanted to say something, and then that is, I really thank Radhika madam and as well as Renuka madam for inviting me to this. So I'm honored that Mutyam Reddy and as well as my another friend, secretary is also a best friend. Yeah. So best friend of mine. So I really thank them also for inviting me. And then see, in any data analytics situation, definitely we have lot of problems, particularly when you just collect data, whether it is a secondary data or a primary data. So primary data, it has to be through a questionnaire. The instrument is a questionnaire, and then from there you just fix a sample size and then collect data. So then definitely when you collect data through a questionnaire, it will be a mix and match of quantitative and as well as qualitative data. So while the secondary data also could be qualitative, quantitative, but mostly quantitative data, like for Reserve Bank of India or any data on temperature or etc. or finances or any bank data, if you want to say that here how the nationalized banks are doing well when compared to the corporate this thing. So here all you can as well do a lot of data analytics of this particular thing. Ultimately, you want to know that here how best I can as well fit a particular model to the data collected or data, the secondary data which you have on that. So whenever you have this type of a situation, so definitely we want to go for ultimate conclusion has to be through the statistical techniques. So one such very important technique is actually a regression. So you know that your regression turns out to be it's a predictive tool. So nowadays a lot of new techniques have come. So that is deep learning techniques. So RNN, CNN. So all these things are also for prediction purposes, and as well as you have neural networks. You have time series modeling, Box and Jenkins modeling. So there are various aspects with which you can as well predict here. So I would like to say that here we have me and my group of students. We have done a lot of research on the comparative study of various methodologies. The standard methodologies are multiple, simple, and stepwise and logistic regressions. And then there are many robust regression. You have many other regressions which you have. Unfortunately, fortunately, these methodologies are not really giving a good insight as compared to the deep learning aspects. So I say that here you start with simple multiple stepwise and logistic regressions for your data aspects, and then you can as well extend it to the deep learning aspects, and then the deep learning aspects are all more suited for the various types of data which you collect. So that is actually a prelude, and then that is what actually we do in most of the data analytics aspects with regard to quantitative data. So what is this actually quantitative data? So quantitative data is of two types. One is it's a continuous data, and then another is actually a discrete data. So people know this, but what actually, how do you define what do you call it, continuous data, and how do you define a discrete data? Most of us doesn't know. So I'll just give a 1 minute introduction of this here. So and then start this particular aspect of simple, multiple, and stepwise regressions. So here, whenever I say quantitative data, which is divided into, you say that you are both discrete and as well as the continuous. So when I say continuous, the data will be collected without any gaps. So when you don't have any gap, we call that as actually a continuous data. So statistically, there are you define on a triplet the data. That's all mathematical and statistical aspects here. So that we don't know, but you should remember that here continuous data means without any gaps. Like for example, you say that your ages in your class, there are 30 students. Their ages are continuous, right? So they don't have any gap. Like suppose if you just take it data on some other context, like number of air accidents taken. So definitely they are not continuous. So they are definitely having some sort of a gap. Air accident doesn't happen every month or every year or every 5 years or 10 years. So whenever you have that type of a situation, then you just collect data.
Pardon me, sir.
Yeah.
Hargopal sir, I think you are going to the next slide. Your slides are not changing, sir.
No, I am not gone. I'm just giving an introduction.
Okay, sir. Thank you.
Yeah. Introduction. So that is what actually you have. Discrete data is the one, like suppose if you are say that you are a product, a company is manufacturing a product, and if it is continuously the product manufactured is having a lot of defectives, so then definitely the data collected will be a continuous defective data. While if you just take it here, if I say that here for 1 hour of my manufacturing, definitely 1 or 2 items will go defective. So then the data collected will be discrete. So in first hour there are 2 defectives. In second hour there is there is no defectives at all, and so on and so forth. So when you have that type of a situation, so then we call that as a discrete data. So then you must be wondering, he has shown it a simple, multiple, and stepwise. He's talking about data type. See, for any data analytics aspect, identification of the data is the crucial thing. It's a backbone. If you do it, see here, this simple, multiple, and stepwise can also be used for numbers 1, 2, 3, 4, and etc. But how meaningful the quotient of determination, that is capital R square, will be, has to be known. Like for example, you say that here, I say that here, babies' growths are dependent on height, weight, and as well as head circumference. So here, baby's growth is actually a quantitative data. Height, weight, and head circumference is also quantitative data. So when I have baby's growth is dependent on all the 3 independent variables. they both should be quantitative. So in the presence of a quantitative independent variables, a quantitative independent variable is predicted. So that is why. So the point number one, the assumption is that here, the data which you have collected is actually, it should be linear in nature. So it should represent linearity. Second assumption is that here, both the variables, dependent as well as independent variables. So that is, growth is dependent on the height the baby grows, the weight the baby baby will be, more weight or less weight, then head circumference. So all the three parameters has to be increasing month-wise. Then only the baby's growth will be estimated. So this type of a situation is taken in simple and multiple stepwise regressions. So therefore, y should be the quantitative variable, and then x1, x2, x3, and xn, so on and so forth, should also be quantitative variables. So these are the basic assumptions with which you just go for a simple, multiple, and stepwise regressions. So then the other thing that I said that, yeah, okay, you are talking about only this thing. So how about whenever I have a mix and match of quantitative and as well as qualitative, like for example, coronary heart disease, right? So a particular researcher wants to know that, yeah, which age group is more prone to coronary heart disease, right? So then he has got the data on age, and then as well as yes, no. So yes is 1 and then no is 2. So that means it is binary data, which is qualitative data. So under that particular circumstances, you go for a logistic. So for any type of data, statistics as an answer, as statistics as a tool with which you can as well infer your data from these aspects here, right? So like, another thing is that here, given a collected a data or having a data set, you should be a meaningful selection of independent and dependent variable. No one says that here, this is dependent on these independent variables, or these independent variables are influencing dependent variable. So you as an intelligent researcher should identify which will be the dependent variable, which will be the independent variable. So these are the aspects which one has to undergo before jumping into computing the simple and multiple stepwise regressions. And as both most of you are, I see that here most of you are doctorates, and then you are all having professors and associate and assistant professors. So you are the faculty of your colleges, and then most of the students also do some sort of a projects, and under that particular context, you should be in a position to see that here how best you interpret the results. So for that reason, you estimate certain things in statistics. What we do is that here we first estimate. What is that actually estimation? Estimation is actually, it could be a population mean, or it could be a sample mean, or it could be a correlation coefficient. So when you estimate and say that, yeah, this is my best estimator. No, we don't say. In statistics, you have two fields. One is estimation and testing. So whatever you test, whatever you estimate, so suppose if I estimate mean, so I should say that, yeah, this mean is the best mean, which I have computed for the data. So then definitely I have to test it. So that test is being done through the null hypothesis and alternative hypothesis. So therefore, the statistical inference of the data which you have collected has two specific fields. One is estimation and another is testing. So if these two are perfect, then only your estimator turns out to be a better estimate. It could be mean, it could be range, it could be standard deviation, and also the error should be minimum if the model fitted is perfect. So these are the aspects which I want to discuss under this particular condition. Right? So this is what actually simple regression. So simple regression is nothing but y equals to a plus bx. So y equals to a plus bx is nothing but it's a straight line. So y is your dependent variable, right? And then in most of the management studies, so you say that your cost is dependent on a particular independent variable. Our profit is dependent on a particular variable. Our demand and supply. So those are nothing but simple regression. So in y equals to a plus bx, y is a dependent variable. A is actually an intercept between y and x, and b is your slope, and x is your independent variable, right? So sometimes even x is also called as in regression predictor and r explanatory variable. R x is your explanatory variable and y is your dependent variable. So if you remember dependent independent, that will be very much useful for you in future to remember also. So then how I evaluate these various parameters which I am saying it. So that is how do I calculate the capital R square, which is called as quotient of determination, and that is being done through the least square method. So, and then multiple regression is the one where, you have one dependent variable and many independent variables. So x1, x2, xn. So that is y equals to a naught plus a1, x1 plus a2, x2, and so on and so forth, an, xn. So there are xn independent variables. The other condition that here, they should be necessarily independent. So then the next question comes is, suppose if they are not independent, they are dependent. So for that also the statistics has got a answer. So that is called as multicollinearity. So you can as well do that sort of a regression also. So that is x1, x2, xn are independent. There is no correlation between them. The correlation is only on y on x1, y on x2, y on x3, y on xn. But if there is a correlation between these independent variables, definitely the regression cannot be fit. The fit will be very bad fit. So hence, you have to have these assumptions intact. Then only you can as well run a multiple or a simple or a stepwise regression procedures. So then you just estimate and then you test for significance. That is by framing the null hypothesis and all. Then the assumptions I have already told, right? So this is actually a qualitative independent variable. Qualitative independent variable is that's what it's a binary 1 and 2. Coronary heart disease, age is dependent on the disease, CHD, yes or no. So that is actually. So and then also you get a error, and that error should be minimum. If it is huge, then definitely how this aspect has to be studied. So those are the aspects which you have here. So these are the things which you have. So like, for example, I'll start with the example. So as a teacher, I first, whenever I want to go for a theoretical aspects, first I understand through an example, and I'm doing the same thing here. A company wants to know the relationship between expenses and sales. So all management aspects goes with it here. Suppose if it is a HR specialization, you want to, the HR guy wants to know that here, what is his salary fixed? So which variable, experience you take it, or the qualification which you take it? So which one is really, if I take it all two, then it will be a multiple regression. If I just take it only experience, then it will be a simple regression, right? So that sort of a thing, expenses and sales. So you name it. In any management aspect, you can as well do that here. It can be done in finances, it can be done in HR, it can be done in marketing aspects, and various specializations you can as well do the regression aspects here. So then forecast sales based on the assumption that the company's sales go up and down depending on the change in GDP. Then the capital asset pricing model. So this is exclusively in finance aspects. Auto insurance premium tables may be built by regressing claim against the demographics, engine size, automobile price, etc. Then regression analysis is used also in compensation to match salary levels. So this is HR aspect. And then usually, you have a dependent variable, usually denoted by Y. So, and then explanatory variables are denoted by X, so also called as independent variables. So this is the beginning of actually a regression aspect here. So these are the various aspects which I foresee and in a management aspect, and you can as well use the regression straight away. So this is what actually you have. So these are the scatter plots. So the before jumping into a simple regression or multiple regression or stepwise regression, you should ensure that you have a strong correlation among y on x1, x2, xn. So this is what actually. So this is linearly related, and then hence this is the better data for regression than this and then this and then other. So this is negative correlation. So even these two are the best aspects, positive and negative correlations. These are okay, but the fit may not be really very good. And this is not at all. So then whenever you have data of this nature, you can as well go for a curvilinear, non-linear regression. Even non-linear regression also, in statistics, you can as well compute. So you know that here this is covariance of xy, sxy, divided by standard deviation of x into standard deviation of y, right? And the ratio of these covariance by standard deviations will give you the correlation coefficient. So you know correlation coefficient, we compute to know the relationship, whether there is a negative relationship or a positive relationship, then only the correlation. So the weaker the correlation, the horrible the relationship is. The best is the correlation, the higher the correlation, you know that your correlation lies between -1 and +1. Suppose if it is 0.9, so x and y are very good, having a good relationship. So if correlation coefficient is high, then regression also gives you a better fit. If correlation coefficient itself is very weak, then definitely the regression gives you a very bad fit. So that is this thing. So for this type of a conclusions, you can as well draw the scatter plot. Right. So as I told you that here, this is actually a simple linear regression. So here beta naught is your intercept. So this is my slope and this is my error. Right. So if I just take it expectation of y, expectation of epsilon becomes 0. So that means I'm just fitting a model thinking that here the error is not there. Right. So I can as well calculate the error also by taking y observed minus y estimated. So that is among the fitted model, how the fitted model y hat behaving as regard to the y. So that I'll do it with the example here. So these are this thing here. So so this is a straight line, and then the slope and beta naught can be taken into consideration. So this is the error term epsilon. So this is what actually we have. The error epsilon is a random variable. It changes from observation to observation. So with mean 0. So the error should be equal to 0. The sum of all the errors which you have computed, that is error equals to y observed. So that is your actual y, and then minus y estimated. So the difference between these y and y hat for each and every observation should be, if I sum all these errors, then it should be equal to 0. The variance of epsilon denoted by the sigma square variance it is. So this is how it is, normal, 0 and sigma. So this is standard deviation. So the value of epsilon are independent. So all the errors which you calculate is independent of themselves. Right? So this is the slope aspect here. So this is the slope of beta 1 is positive. So the other way it is, it increases, then decreases, then slope is negative. If it is starts with low level of this thing here, x-axis, and then as it progresses, the x progresses, then definitely expectation of y will be increasing. So this is, the slope is positive, slope is negative. So when it is perpendicular to x-axis, it will be slope is 0. So that means the relationship between y and x is very bad. So that is what actually we have the other aspect visually. So, so now we want to estimate the regression line. So by principles of least squares, we just take it here. Yi is your observed value, the actual value, and yi hat is your estimated value. So this is also dependent variable of observed values. So that observed values is the given values. So this should be minimum. The error sum of squares should be equal. So how I say error sum of squares? Yi minus yi hat is error. Sum of all these things, a whole square, should be equal to 0, minimum. So that is how. So even if it is not minimum, but the value is very less, so that means that actually the least square error value is very less, then definitely we have a very good fit is very good and the error is under control, right? So this is our so minimum errors square will be like this here. So a slope of the estimated is this is how you just calculate estimated regression equation, and then y is the intercept of the estimated regression equation. So this is a y bar minus b1 x bar. So the intercept is estimated as this mean of dependent variable and a mean of the independent variable, and then the slope value is calculated the covariance xy by variance of x. So the ratio of this covariance by variance of x, you will get the slope estimated, right? So then, so this is actually a simple example. See, this is only for a pedagogical example. So anyone will say that here for only 5 observations, if you fit this thing, it is not acceptable. So you have to have at least a minimum is 30 observations. So only for demonstration purpose, I have taken this here. So for actually a case study, this thing through SPSS, I will demonstrate after the lecture, right? So this is TV ads. So and a number of cars sold. So the this particular company, Kumar's Electronics Periodical, has a special week-long sale. As part of the advertising campaign, Kumar runs 1 or more TV commercials during the weekend preceding the sale. Data from a sample of 5 previous sales are shown below. So these are the 5 this thing here. So now with this, he wants to know that here, if I want to increase X, so that is number of TV ads, will my car sales will be doing it more or not, right? So this he deals with this. Kumar deals with electronics and as well as the automobile industry. So he wants to see that here how many ads will increase the car sales. So that is actually you want to know. So that this is actually TV ads. So I'm just fitting a linear regression, right? So I have taken sum of these x's and then mean is 10 by 5, it is 2. Then number of cars sold is this, y. So I've just added this 100 by 5, it is 20, mean is 20. Then I have deviated from average. So that is 1 minus 2 is minus 1, 3 minus 2 is 1, 2 minus 2 is 0, like that. So deviation of x is being taken, deviation of y also is taken. So 20 minus 4, 14 minus 20 is minus 6. Yeah, Abdul Sattar, you have raised the hand. Yeah, you can ask. Abdul Sattar. Okay, by mistake it is okay. So y minus y bar. So that is 14 minus 20, it is minus 6. 24 minus 20 is 4. So now I multiply this minus 1 to minus 6, it is plus 6, like that. And then I have taken the xi minus x bar whole square. So now I just calculate the slope. Slope is the sum of this 20 divided by this total 4, right? So 20 by 4 is actually 5. 5 is my slope. And then this is my intercept. This intercept is actually y bar minus b1 x bar is 20 minus 10, it is 10. So y hat equals to beta naught plus b1x equals to 10 plus 5x. So this is my working equation, y hat. So now predict sales if ads run 5 and 50. So now I can as well do that here. Suppose if I say my x is 5, x is my TV ads. So it is 5. So 5 means 25 plus 10, 35. So if I advertise 5 advertisements, then 25 cars can be sold. Suppose if I increase x to 15, so 75 plus 10, 85. So 85 cars can be sold when x is 15 advertisements. So that is how the future predictions can be done under this particular case here, right? So this is our R square. Now I just want to know the relationship between advertisements and the cars sold. So how better it is. So for that, this is how you just calculate. So this is sum of squares of total equals to sum of squares of regression and sum of squares of the error. So yi hat you have, now the estimated values are there, minus y bar whole square plus summation yi minus yi hat whole square. So this is from here you can calculate the total sum of squares and then say that here how much it is. So that should lie between 0 and 1, right? So the higher the value of r square, the better the fit is. So that means there is a good relationship between the sales and as well as the number of advertisements here. So that is how you can as well comment or conclude the experiment. So now I'm just calculating the whatever these are there. So that is being calculated here. So this is your sum of squares, total sum of squares, and this is the regression sum of squares. So I take a regression sum of squares by 100 by 114, I get r square. That's what actually I do. So 100 by 114, it is 0.87. So r square is lying between 0 and 1, and r square is very good. It is 87.72. So that is the regression relationship is very strong, right? Of the variability in the number of cars sold can be explained by the linear relationship between the number of TV ads and the number of cars. Right? So this is how you just calculate, and the 0.94 is your correlation. Square root of 0.8772 gives you the correlation coefficient. So that is the TV advertisements and cars sold has got a high amount of relationship. So if you increase the TV ads, cars will be sold more. That's what actually the ultimate idea. But I have estimated r square. Now I have to test this, whether this is a very good fit or not. So for that, I just go for what is known as the analysis of one-way classification. So that is what actually we do here. Before going to that analysis of variance, we just calculate the standard error of estimates. So that is mean square error. Mean square error should also be less. So that mean square error is taken as square root of MSE. That is sum of squares of error divided by n minus 2. This is the degrees of freedom, right? So this also we can as well calculate from this standard error of estimate. So the standard error of estimated for these for the formulas given in the previous slide, the same thing for the example is being computed. So the error is what actually the mean square error is actually 14 by 3. And then S is square root of 4 by 3. So that is 2.16. So around 2% error. So 98%, it turns out to be very good model fitted. So mean square error is very less in this particular case. Suppose if mean square error turns out to be 21 or 25, then your model fitted is very bad. So the lesser the mean square error, the model fitted is the best. So that is what actually you should conclude of your experiment for the data collected. Right? So then these are the properties. So if I just take it beta coefficient of x on y and beta coefficient of y on x. So if I multiply this, I just get the square root of this thing, the correlation coefficient. So this is actually a geometric mean between the regression coefficients. If one of the regression coefficient is greater than unity, so that is greater than unity, so then the other must be less. So if one is greater, the other should be less. So that is the other regression coefficient. Anyhow, nowadays these are not necessary. If it is fit is well, all these properties will hold for the data collected. So regression coefficients are independent of change of origin but not scale. So right. So when it is regression coefficient is what do you mean by this here? So if you change the origin, so that is if I have data on pounds, if I change the origin to kgs, you need not do. But scale measurement, this thing, you have to convert that here. Right? That's what actually we have here. So then testing the regression line. So testing the regression line is what actually we set up an null hypothesis for the beta 1 and beta naught. Both I tested by the t-test here. And that t-test and f-test, we just do that here. F-test for capital R square and t-test for the individual this thing here. Like for example, in this simple regression, what is the t-test? T-test is nothing but for the number of cars sold number of advertisements, number of advertisements, and Y is your cars sold. So t-test is done for the the number of advertisements X. So that's what actually we have. So H0 equals to beta 1 equals to beta versus alternative hypothesis is that here not equal to beta. So I just compute this. B1 I have minus beta and by standard deviation of beta. So this is n minus 2 because there are two values involved. So that's the reason I'm subtracting n minus 2 degrees of freedom. So this is how you just get it here. And the p-value should be less than 0.05. So that's what actually I just calculated this here for the same example. Y hat equals to 10 plus 5x. So I just, there are 5 observations. 5 minus 2 is 3 degrees of freedom, right? So S beta 1 is 1.08 and the test statistics is 4.63. So for 4.63 and for 3 degrees of freedom, 0.05. 0.05 is here, 5.841. So 5.841 is less than 4.63. So that means T is T calculated is 4.63 and T tabulated for this thing, it is 5.841. Suppose if I just take it twice of this 4.63, if I just take it here, so that is you test it at 5% or at one tail. So only if I just take it the right tail as I've shown it in the this thing, so it will be definitely greater than this thing here. So single tail, if you just take it here, 0.025, it is 4.63 is my calculated value. And then my tabulated value is actually T calculated is greater than, T tabulated is greater than the T calculated. Hence, there is a significant linear relationship between X and Y. So we are accepting the null hypothesis. So that means X and Y are related better. That's what actually it amounts to. That is, the X is needed to predict Y. So number of advertisements is definitely directly proportionate to the number of cars sold. So that's what actually it amounts to. So similarly, for overall R square. So how do I do that here? So that is being done. For multiple regression, F test for overall significance, while the T test is used for test of for each coefficient. So each coefficient, how we test it is being seen there. For multiple regression, definitely F test for capital R square. So that is how you do. I'll show you the one real live example. So then you can understand. So this is how you do this thing, right? So this is how this is also cause and effect relationship is present between X and Y. So just because we are able to reject H0 null hypothesis, then there is actually does not enable us to have a statistical significance. So that means there is a linear relationship between X and Y. So that's when you accept H0, there is a linear relationship. When you reject it, there could be a cause and effect, and then how much of cause and effect is being done by the R square value. Right? So this is how there are various examples: drug X cure Zika, whether or not discrimination leads to wage differences, what factors make corporations earn higher profits. Statistics provide information about association. So association is nothing but correlation. Association can always be spurious. What is this spurious? If X and Y are independent of each other, right? X and Y are independent of each other. Like for example, father's heights and sons not belonging to these fathers, you will get still a correlation, but it will be a spurious correlation. So that means to have a good correlation, X and Y should be related. If X is independent of Y, then definitely you get a spurious correlation. So that sort of this thing, relationship should be there. So that cause and effect. So how they are changing it with the various causes, there is actually an effect or not when you are doing it. So then it's a positive correlation which you have. So then next comes is the multiple linear regression. So as I told you that here these are the beta naught, beta 1, beta 2, beta p. We don't have on hand. We have only data on Y, X1, X2, and XP, right? So beta naught, beta 1, beta 2, and beta p are called as parameters. And this is your error term, right? So you have multiple variables. So the relationship of multiple variables is dependent on y. So these are explanatory or independent variables, x1, x2, xp. So now, so this is the question here. So how much of a relationship is there? Is it, say I told you that here, if it is 0, r square turns out to be 0, very bad relationship, right? And then, I mean, all independent variables are not dependent on y. Suppose if it is 0.8, so then there is a very good relationship, 80% relationship between dependent variable and independent variables. Also, so that is one parameter which you have estimated, capital R square. But which of these independent variables is influencing y? So that is being done by, that also is being done. So which one is significant? If this is significant, then really x1 is needed to predict y. If x2, so like this is, I say that here, this is height, weight, and head circumference. Suppose 3 variables I take it. And then growth. Suppose doctor gives you some 30 observations of, for each baby 4 observations are given. Height, weight, and then head circumference, and as well as the, growth. So y is there, x1 is there, x2 is there, x3 is there. Now, overall it looks to be 0.8, right? But doctor feels that here all 3, okay, it is giving good this thing. But I would like to know that here head circumference is really needed to predict the growth of the baby. So then I have to test each individual variables, right? Whether all 3 says this is influencing the growth, then definitely you say that here it is a good this thing. So, but in most of the cases, 1 or 2 variables might be dropped. So then how do I test it? So that is being done through the t-test. And overall also R square is also 0.8, I said. So that also is being tested by ANOVA single. So that is how the multiple linear regression goes into. So this is actually the equation that describes how the mean value of y is related to x1, x2, xp. So how this relationship of y on dependent on growth is dependent on height, weight, and head circumference. It could be many also. So then I go for estimation, the multiple linear regression. So I estimate for these parameters, I estimate the values. This is my intercept. So these are the various sample statistics which I just compute for the multiple linear regression. So that is how it is. Multiple linear regression model is this here. So you have sample data, and then for this you estimate the multiple linear regression, then provide estimates to this, and then that will be the fitted line. So that is how you do it. And then here also we have to minimize the error. So that is what actually the formulas for the regression coefficients is so and so matrix algebra. We normally rely on computer software packages to perform the multiple linear regression. Say by hand you cannot do this. So this is one example of multiple linear regression. Then see here, this is actually a software firm collected data for a sample of 20 computer programmers. A suggestion was made that regression analysis could be used to determine if salary was related to the years of experience and the score on the firm's programmer aptitude test. The years of experience score on the aptitude test and corresponding annual salary is $1,000 for a sample of 20 programmers is shown on the next slide. So this is what actually the data is. See here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, right? So this is experience, score, and salary. So here, that's what actually I'm just saying it. So here, you may not be in a position to know that here, which is independent one and which is dependent one. So you should be intelligent enough saying it. So you say salary is dependent on experience of that particular candidate and as well as the score he has scored in the test, right? So now the HR person should fix if which one is really causing more in terms of experience and as well as score. So now I just do this thing here. So now the model turns out to be y equals to beta naught, beta 1 x1 plus beta 2 x2. So as I told you that here, y is annual salary for $1,000, $1,000, and x1 is years of experience, and the score on programmer aptitude test is x2. So now the model turns out to be a multiple linear regression with 2 independent variables and 1 dependent variable, that is your annual salary, right? So now I want to fit this here. So now I have, this is my input data, x1, x2, and y. So for all the 20 candidates who has appeared for the exam and with some experience and as well as their salary. So for solving multiple linear regression problems, I want to estimate beta naught, beta 1, beta 2, and R square, etc. So now, so this is actually, so SPSS regression quotient equation output is this. Intercept, so that is beta naught, this is beta 1, and this is beta 2. So this is the coefficient, this is a standard error. So this is the, T statistic, right? So intercept may be significant, may not be significant. We don't bother about intercept. It's a constant value because it is not related to any variable given. So hence this p-value should be less than 0.05. This is greater, so this is not significant. But intercept should be there in the equation. If you just take it experience, yes, it is significant. It is less than 0.05. Right? So 0.5019. So it is less than significant, less than 0.05. So even test score. So in this case, to fix the salary of these candidates, both the experience and test score has to be taken into consideration. If he has got if the candidate has got a lot of experience, then he should do test score also better. So if test scores are very poor, so that means that actually test score is not the one which is influencing the salary, right? So here both are significant because this is called as the probability value, computed probability value, so which is less than 0.05. This is also less than 0.05. Hence, these two independent variables are influencing the y. So this is what actually salary. So this is my future. If I just take it, another guy comes to my company, and then if I say that here he has got 12 years of experience, so experience will be 12, and then his test score is 86. If I say 86, so then if I can calculate the salary of that particular. So that is what actually, this is a working equation for the future people who come into that particular company, right? So as I told you that, yeah, this is change in y, etc. So this is all I've already told. So with that, I just calculate 1.404 is my thing. So 1,404 for each additional year of experience when the variable score on programmer aptitude test to held constant. So then beta 2 is 251 for each additional point scored on the programmer aptitude test when the variable years of experience is held constant. So these are the two which we have estimated. So then I just calculate the relationship among y and as well as the two independent variables. So by this particular formula, and then I just get this is my ANOVA. That's what actually I just typed. So R square multiple R square, whether it is significant or not. Yes, this is less than 0.05. So almost it is 100% significant. So that means actually the R square which you have computed turns out to be a very good fit for this particular data which you have collected and analyzed it here. So this is what actually the R square is 83%. The relationship between the salary and as well as experience and test score is around 83%. And this is estimated, and this is being tested by ANOVA, and then it is very good this thing which we have. So adjusted R square is also modified version of R square. So this also directly gives in this thing here. So that is how you just do the this thing here. So I'll just go to a example and then go for the other, or else I'll just directly go. These things I just calculate always the same way. We just calculate the t-test and f-test. Right? T-test and f-test I just calculate. Then regression estimates will be taken into consideration. So this is this is another aspect qualitative independent variables. That is, I say qualitative is actually a logistic regression. So that is, you do this here. Yeah. So, so what is qualitative? This thing. This is yes, no. Yes, no is your qualitative data. So for this also we can as well do the this thing. So this is called as dummy regression. So dummy regression is a dummy is what actually dummy is the degree 1 to 1 or 0 1 0. So that is how you can as well do that here. 1 or 2 variables only can be dummy. So that's what actually x3 is dummy. 0 if individual does not have a graduate degree. 1 if individual does have a graduate degree. So this is called as the dummy regression. Same way. So here you just see here whether he is a graduate degree or not a graduate degree, it is not influencing. So that means actually you can as well eliminate that particular variable. So this variable degree can be, you can as well eliminate. So degree is not playing a role in salary fixation. That's what actually it amounts to. Right? So that is what actually you have under dummy regression. So then you have qualitative variables which you can as well calculate the standardized residual, the residual scale plot also we can as well do. So these are all within the range, but this is going outside this particular range. So the predicted salary looks to be quite high for this guy. So then you just go back and then see that here why this error is quite high, right? So his test score is high, so then definitely he has got this thing here. So the next is actually, this is called as the stepwise regression. So this stepwise regression is really very good regression it is. I mean, you need not eliminate, the method itself eliminates the independent variables. So that's what actually, y may be dependent on many independent variables. How to find a subset of x's that best predicts y. So there are several criteria for that. Adjusted R-square, Akaike information criterion, or Bayesian information criterion, likelihood ratio test. There are many methods with which you can as well say that here it is that. So this is available in the statistical packages only. We cannot do it by hand here. So in this stepwise regression, we want to find the best set of x's to predict y, right? So functional characterization of the true causal relationship between y and x can be also taken here. Right? So this is about stepwise and this thing here. So as I told you that here, logistic also it can be taken two alternatives, or it could be ternary, right? So that is middle income is 1, higher income is 3, 2 middle income, and the lower income is 1. So the 3 categories, it's a ternary. So that is how you can also do that here. So here we just calculate it. So this will be a sigmoid curve, and then this will be non-linear as compared to the linear regression itself, right? So this is what actually we have here. So I'll just go to computation aspect, case studies, right? Okay. So this is, are you seeing my screen? No?
It is visible, sir.
Data sheet. Yeah, data sheet is visible, right?
Yeah, now it is visible.
Yeah. So this is actually 12 observations. So a company wants to know that here, this particular situation, the company wants to know that here, profit is dependent on all the 3 advertisements. So therefore, obviously, profit is actually a dependent variable y, and a paper advertisement and TV advertisement and radio advertisement are independent variables. So when you have this, how best I can as well predict profit for future radio advertisements and TV advertisements, etc. So I just, in the initial stages, I'll just take it through SPSS. I'll just say, I'll just take it profit as my dependent variable. I just take it only radio advertisement. So this is simple regression, right? So I just calculate statistics, confidence interval, descriptive statistics, at partial, and then also collinearity. So collinearity doesn't come because only single variable. So residuals, Darwin-Watson scale, and case-wise results. All these things I can as well have it. Then plots I can as well have. So that is dependent is on y-axis, and then z predicted. So the future value I can as well have. Whether the data is normal or not, I can as well test it. So then options, yeah, 5%. Then I'll say okay. I got it. So this is what actually you just see here. This is descriptive statistics regression, right? So I have this is average profit 70.667. This is advertisement one, so that is radio advertisement. So it is around 30 average. Then 14 is the variation in all the 12 months. And then this is 12.79 is the 12% variation is there in the radio advertisements. The company has got. So then I wanted to build a relationship between profit and advertisement. So how much of radio advertisement is involved in the profit for the company? So it is 0.865. So 0.865 means what actually 86.5% profit is being acquired by the radio advertisement. And then I have estimated this, I have tested. And then when I tested, so this is once again a t-test. 1 minus r by square root of 1 minus r squared. So that is r into square root of n minus 2 by square root of 1 minus r squared. So that is being the t-test which is done. And then this is 100% significant. So that means, so good relationship between. So both are related with each other. Profit is related with regard to the radio advertisement. So then after calculating the correlation, I just went to and calculated this. So it is 0.747 is actually 74.7% good relationship. So fit is around 74.7%. So that means R square value is quite high. And then now I have estimated R square. Now I want to test it. And then I have seen ANOVA, I have done it, and then 100% significant. So that means the estimated R square turns out to be very good. And yeah, Amit Kumar Das, yes. I don't know, by mistake or okay. So this is 100% significant, 100% significant. So the model fitted turns out to be very good, right? So then after that, I have the quotients. So that is the quotient is beta naught, and this is beta 1, right? This is standard error, and then both are 100% significant. So that means relationship is there with the radio advertisement. The profit is around 74%. That's what actually we can as well have. So the residual statistics are also calculated, and then the visualizations are being seen. So data seem to be normal in nature because mean is 0, standard deviation is 1. Right? So then also you just see this is a normal probability plot. So around this line, this
result
yes.
chart is not visible.
Yes, results are not visible. Okay.
Yes, sir. Only your data sheet is visible. Result chart is not visible.
I'm sorry. Now is it visible? Now is it visible?
Yes, sir.
Yes, sir.
Yeah, please. Yeah. So see here once again, I'll go back for the analysis interpretation. So this is profit 70.667. Advertisement is 30. Standard deviation is 14.54 and 12.79. The correlation quotient is 0.865. So that means the relationship between Y is what actually it is profit, and radio advertisement is X. So the profit gained in all the 12 months seem to be around 86%. Good relationship, and it is estimated 0.865, and then it is also tested by the t-test, and then it is 100% significant. Hence, it is actually having a better relationship between these two. So profit and radio advertisement has got good relationship. Then I have estimated R square 0.722. Sorry, this 0.747. So Y and X are very much related, around 74.7%. And then I have estimated R square. I have tested this by the F test, and then it is 100% significant. So that means the line fitted for this particular 12-month data turns out to be very good. So then I have just calculated the beta coefficients by t-test, and then both are 100% significant. So then I just got these things evaluated, right? So this is the visual representation, and then fitted line, the PP probability plot. So these are the actual observations, and this is the fitted line. It is a straight line. Assumption also is being stated. So this is the scatter plot of these this thing here, standardized predicted values. So how they are scattered. So that's what actually you can do under these particular condition, right? So now I just go to for the same data, I just go for a multiple linear regression. So I'll just go to regression, linear. I include the other two, TV advertisement and as well as this thing, right? So I just calculate this. So I've calculated all that profit is dependent and independent variable, advertisement 1, 2, 3, and so on and so forth. See here, advertisement 1, 2, profit. Share this. Yeah. So correlations also is calculated. See here, if you just take it, profit and advertisement 86.5% related, profit and advertisement to 0.395. So as he advertised with the other advertisements, the relationship seemed to be lessening. So that means that actually all three he can have, or only one thing he can have, radio advertisement. So that you can as well decide by seeing this particular this thing here. See here, 0.973. R square is 97. With radio advertisement, it is 74%. But here it is increased with all multiple linear regression. And then I have estimated 0.97%, 0.97.3, and this is tested, R square is tested. It is 100% significant. That means all the three also influencing the profit for all the 12 months. So then also I have estimated the quotients, beta quotients, and then you just see here all are significant. To get a profit, a radio advertisement is needed. Then radio and what are the things? Radio advertisement, not given there. Radio advertisement, and then newspaper advertisement, and as well as the other advertisement. 3 advertisements are needed to predict the profit for all the 12 months. So that's what actually it is being done, and then the visualizations have seen it here, right? So, but after this data is analyzed and shown it to the businessman, business says, I don't want all three. I want to cut short something else. So hence, I just go for what is known as the other technique called as the other technique called as what actually it is actually a stepwise regression. Right? So here enter means multiple linear regression or simple regression. I just go to the stepwise regression and then compute. So I have computed this thing here. So these are the correlations for all the 12 months, right? With all this thing here. See here. So the difference between the multiple linear regression and stepwise regression is that here, advertisement 1 with advertisement 1. So that is simple linear regression. It has been calculated. 3 models it has fitted, right? So 3 models it has been fitted for the dependent variable profit. Right. So the 3 models R squares are there. So it is actually advertisement 1, radio advertisement. The R square is 74%. Right. with the advertisement 1 and 2, it is 90%. With all the 3, it is 97%. Right? So I have estimated these R squares, and all these R squares are being tested by ANOVA. All are really good this thing. So now you can say that here, and then we have also estimated, and all are significant. All are significant except these constants. That is okay. All are constants. So that means that actually all the models. See here in the first model, and only advertisement 1 is being taken. In the second model, only advertisement 3 is being dropped. Right? All models, all permutations and combinations are being run by the stepwise regression, and got this here. Suppose if he wants to advertise only this thing, his profit will be around 74.7%. Only he is doing it only advertisement 1. If he wants to have a share of 2 advertisements, advertisement 1 and 2, then his share is around 90%. If he can if he withholds the third advertisement, it is 90.3%. Suppose if he wants to do all, 97.3%. Right? So now the ball is in the businessman's court, and then he has to decide whether he wants to have 90%. Then he can as well cut the profit of the third advertisement. So he cut the third advertisement cost, and then only run the business with only 2 advertisements to get a profit. So that sort of this thing is possible in this particular situation. So this is how you can as well do the various permutations and combinations under the stepwise regression. While in a multiple linear regression, all the variables are taken into consideration. Right? I'll take another case study. Any questions here? Any questions here? There are 387 participants. Any questions here? Okay, I'll just go to the other this thing. I have many case studies. Just right. So this is the okay. So this is I'll share this. Yeah, this is another this thing here. So here this is another multiple linear regression. So the consumption of oil in gallons is dependent on the temperature of that particular day, and then as well as with the insulation which you do. So let us take it this year. So you have to be very careful in selecting the variables which is which one of them are dependent. So here you say that here consumption of oil in gallons is dependent. Temperature and insulation, I just take it as the independent variables. It's a multiple linear regression. So enter, I have done it here. So then I'll say, okay, I just got it here. You just see here, R square turns out to be 0.96%. So that means the consumption of oil in gallons is definitely dependent on the temperature and as well as the insulation. So if insulation is bad, then definitely it might be different. And then temperature, if it goes high, then it will be different. Yeah. So that means, so this is overall, it is significant. And then individually also, it is 100% significant. So this is how you do that here. So this is for the multiple linear regression. Suppose if I want to do it with the other one. So the other one is that here, stepwise regression. So I'll just go to the stepwise regression and then do that here. So how best you'll get it here? So yes, I got it here. So R square turns out to be 75% with only temperature. And if temperature and insulation is there, 96%. So if you just take it only temperature, it only gives you around 75% of oil in gallons used here. Both are significant. So it has fitted two models, model 1 and model 2, with the independent variable. This turns out to be a simple regression. And then this is a multiple linear regression, which we have done it under the multiple linear regression also. So that is how you do that here. The coefficients and etc. are being tested also. And then they are all 100% significant. So this is first model and this is the second model. Right? So these are the coefficients and then they are tested and then they are significant. Yeah, so this is how you get the other thing there. Right? Okay, so this is what actually we have here. Yeah, so then I want to take up another example here. See here, then similarly age and BMI, then exercise, right? So etc. So then drug A, drug B, drug C. So like that you can as well try and then see that here. So BMI, like for example, if you just take it this year, BMI, is it dependent on the, so suppose if I just take it, I'll reset it. Yeah, I take it BMI is dependent, then I'll say age, and then fat free number. So fat free number, how much of fat it is there. If fat is high, also BMI also will increase. So I'll just run it a multiple linear regression. So I just got it here. So R square is 0.670. So this is good enough or not is being tested by, so this also I'll share it. Yeah. So this is what actually here is around 67%, and whether it is significant or not is being tested by ANOVA. It is 100% significant. Then the quotients also is being tested. So here you just see here, age is not saying it. BMI will increase. See, this is not significant. Age is not significant. So age is not necessary to predict BMI. Only the fat-free number is the most useful. That's what actually it amounts to. Okay. So same, even your stepwise regression also says the same thing. You just see here. I'll show you. Analyze regression linear. I'll just go to stepwise for the same this thing, stepwise regression. You just see. See here, this is 0.661, right? So fat-free number with only one independent variable, simple regression, 100% significant. It is 66.1%. Then if you just go to the other model, so even fat-free number is actually more significant. Right? Then excluded variable is the age in this model. Then the other variable is not, when it is excluded, it doesn't give you that particular this thing. So that is the difference between a stepwise regression and as well as the, sorry, I think I have to share this also. Output is shared. Yeah, so this is how you can as well do the aspect of this here. So I'm done here, Madam Renuka Madam and as well as Radhika. So I'm done, and if you have any questions, I can as well ask. I can as well answer. Any questions from the participants? I have a lot of chat.
Dear participants, if you have any questions, you can unmute yourself and ask questions to sir.
One by one, you please ask.
Please, one by one. Go. Dear participants, please unmute yourself and you can ask questions to sir. Sir, in the chat box, there are some questions, sir.
No, only PPT sharing they are asking. That's it.
No, sir. Sir, one question from Saurav. What is the difference between adjusted and normal R square?
Yeah, adjusted is always less, and then the normal R square will be high. Adjusted R square is always less. So 1 minus of, almost the ratio will be the different. But adjusted R square, we don't take it. Only the actual R square will take it. It gives you that. So always adjusted R square is less than the actual R square. If you want it, you can as well take it, but normally we don't take it. Yeah.
Sir, there is one more question, sir, from Dr. Srinivasa. Sir, when the regression techniques shall be used for what type of data and for what type findings? Please clarify.
Yes. See, regression process is actually meant for quantitative dependent with quantitative independent. So, because it will be meaningful if you have independent variables which are quantitative in nature, you can predict a quantitative variable. I cannot predict a qualitative dependent variable with quantitative measurements. It is meaningless. So for simple regression, multiple regression, and stepwise regression, these dependent and independent should be quantitative in nature. That means it should be interval data or ratio data. So then only it can be used. Otherwise, it cannot be done. But if you, if Srinivas says that here, no, I have some qualitative data. So then I say that here qualitative data and quantitative data, you just go for a logistic regression. Right? That is.
There is one more question, sir, from Marun Ahmad. If there are 3 independent variables, then what type of regression is used?
3 independent variables and as well as a dependent variable, then multiple linear regression.
Yes.
Suppose if these 3 are not independent and they are dependent, you have to go for a what is that actually called? Multicollinearity. Multicollinearity has to be studied.
Sir, there is one more question from Dr. Anjum. Can regression be used with mediating variable?
What is the mediating variable? She should be clear in saying what is mediating. Mediating, is she talking about interaction, interactive variables? Yes, if they are interactive variables, if they are independent, yes, you can as well do that. So mediating means what actually it comes in most of the economic data, interaction data. Like in management, suppose if I say that here LG is one who is selling it the refrigerators, then I have another Kelvinator, I have another model. So they become independent. So but the ultimate product is the refrigerator. Yeah, you can do that.
Sir, one more question.
Yes.
Please clarify the regression analysis can be accessed without SPSS.
Yeah. Multiple linear regression, up to multiple linear regression, you can access with MS Excel. Simple regression, multiple regression can be accessed through the MS Excel. But stepwise regression, no. Stepwise regression cannot be accessed through MS Excel.
So one more question from Dr. Rishi Kumar. How to create a classic analysis and its interpretation in SPSS?
Classic analysis. What is classical analysis? If he is there, he can as well answer. Ask me. Classic analysis. What classical analysis? Cluster analysis is he talking about?
I think so. So he mentioned classic analysis. Dr. Rishi Kumar, sir, if you are unmute yourself, you can clarify your doubts, sir, directly.
And someone said Excel, the output in SPSS can be exported to Excel also.
Okay.
Most of you have asked what type of data. Both should be quantitative data. Then only you can also use regression. How to create classical analysis and its interpretation in SPSS. Classical analysis, no, I don't know what he meant is. Rishi Kumar.
The participants can unmute and ask the questions.
I am asking about the cladistic analysis, phylogenetic tree in SPSS, how to make this, and where I got how to interpret this. That I am asking.
No, tree. You are talking in terms of tree construction.
Yeah, cladistic analysis in basically in taxonomic work.
No. So for that you have to go for a support vector machine. SVM you have to try. Regression doesn't give you. In taxonomic data, you have to go for a support vector machine, or you have to go for a neural network aspect.
I saw the options in the SPSS that to make the cladistic tree in SPSS. So I am asking if there is any
tree for that can be done in AMOS, SPSS AMOS, AMOS.
Okay. Sir, is there any link or any video of that? Please share in.
No. AMOS and SPSS are paid softwares.
Okay, sir. Thank you.
But AMOS will give you this tree. Yeah.
Hello. Good morning, sir.
Yeah.
Yes, sir. This is Dr. Anurag. Sir, my question is this: that how we use the Durbin-Watson tests here in this regression, and also get one of the table which is explaining the residuals. So how we interpret that thing?
Yeah,
so
correct. See, Durbin-Watson statistic is being computed only for the error. See,
okay,
error
sir.
you calculate y minus y hat, right?
Yes, okay.
So whether this is significant or insignificant. Suppose if it is significant, that means actually error is little high.
Okay.
Suppose if Durbin-Watson statistics is insignificant, that means the error is within the control. Mean square error is within the control. Yeah.
Okay. So, sir, that table, can you please explain it with the on this sheet, on this data set?
Yeah.
How?
It is there. I've done it right. Durbin-Watson, I'm not given that much of importance there. Anyhow, I'll just show you.
Yes, sir.
Linear. See this only. I'll just take it. So I'd say option statistics. See Durbin. This is for residuals only.
Okay.
So I'll say okay.
So also we test the collinearity test, sir, here.
Collinearity is single both variables. Yeah, collinearity also we can do. Here it is there.
Yes. So please interpret. Please interpret.
Yeah, linear. Then you say option.
In statistics, I think.
Statistics. Collinearity.
Yeah,
1 minute.
Yes. Yeah.
So continue. So I'll say okay. See here, you'll get it here. So here you just see.
Yes, sir. This residual statistics, how we interpret it, sir. Yes.
That's what actually I told you, no? See here, residuals are all negative, right? Mean is zero. Standard deviation is 2.48. So then definitely it is mean zero means what actually? All errors are within the control.
Okay.
Normal, I shown you, no? Normal 0, 1. It should be. So it is 2.48. So variation among the residuals, it is there. But average itself is 0. See here, standard predicted value is 0. Standard residual also is 0. That's it. So it is standard predicted value is 0 and 1. It is normal. So that means the fitted line turns out to be better.
So then after we have to apply, find out the normality in residuals, we have to find out that, sir.
No, this is normal only. Theoretically itself is normal. So you can draw the predicted value, this thing under these things. You just go here. Regression. you can as well predict here, linear. See here plots.
Yes.
So here predicted, everything is there. Right? Whatever you wanted, see dependent is Y, then
Yes, sir.
Z predicted is this. You can as well do histograms, normal probability plot, continue. Okay, so it will come. See here. So normal, it is normal. Now mean 0, variance is 1, standard deviation is 1. It's normal.
Yes, yes,
So
yes.
this is one chart. This is probability plot and the scatter plot. This is how it is. You can as well get it.
And sir, generally we select Z residuals in Y, sir. You have selected dependent for that reason. Is there any difference in that?
No. See, normally what is it actually? You have Y and Y hat, right?
Yes.
See, Y should be on the Y-axis. Y hat is if you want to compare these two. Normally, X-axis is actually your independent variable, and Y is your predicted value.
Yes,
So the
yes.
difference, yeah, that's it. Because you say that your X and X, what is that error? So I have taken error as this thing. E equals to Y minus Y. That's all.
Yes, yes. So then the collinearity from the table. How could we find out the collinearity? Just to the table.
See, collinearity I have shown it. No? So collinearity you just see here. Residual statistics, model summary. Yeah, collinearity diagnostics. See, condition index is 1. Eigenvalue is 1.688. Right? So variance you just see here, variance proportions. Constant is 0.16 and then the second variable, independent variable is 0.84. So if these are high, right? If these are high, see what is the collinearity? X1 and X2 should be independent, right? So in this case, only you have what actually BI, single variable you have. No, collinearity index, I'll show it for the other example. Because here it is single independent and single dependent. Fat free also there, but it is fitted only one. No? So X1 and X2, it is not taking it. Only X1 is only it is taking. For that, collinearity diagnostic is being taken. So at least you should have 3 variables which are in the analysis. So that I'll show you 1 minute. For another example, I just take it. See, I just go to regression, linear. So fat free. See, I say that I'll reset it. Right. So here is dependent on drug A, drug B, drug C. Right. So I say options. Continue. Statistics. I say collinearity diagnostics. Then Darwin Watson. Continue. I'll say okay. See here. See, R square is so low, it is 0.321. And then this is estimated R square, and then this is the significance. It is insignificant. Right? So the quotients you just see. The quotients also you just see. The model is very bad. Model is very badly fitted. Right? So I just go for it. See here. Because of this, drug A, drug B, drug C, they are variance proportions are 0. That means they are no variation. All 3 turns out to be the same. So they are not independent, but there is a dependency among drug A, drug B, drug C. That's the reason it is very low variance proportions. Got it? In the previous case, it is 0.84 and 0.14 and all. So here it is almost 0. At the third dimension, it is 8.85. But in most of the dimensions, the variation is almost 0. So that means that actually drug A and drug B and drug C are same effect on the beer. So there is actually multicollinearity. They are not independent. They are dependent. Drug A and drug B, drug C are dependent. That's what.
So this citation index, what should be the value for that reason?
Which citation index?
In collinearity index, it is 1, then 19, then 28, then 75. What
Yeah,
it
that's
is?
what actually. So it is index condition index it is. See, so in the first dimension, it has started with 1 and it has gone up to 75%. It is like an eigenvalue sort of a thing. It is.
Okay.
It is increasing. Yeah. So that means it is the strong collinearity among truncated rugby drugs.
Pair of planes को represent कब करता है जब ABC plus 2FGH
Very low. Your voice is very low.
minus BG square minus CH square बराबर 0 है। अब हम कह रहे हैं ये कौन को रिप्रेजेंट करेगा हमारा? ये हाँ लिख दिया भाई, छूट गया नहीं पेन चला होगा। ठीक है, तो ये अगर 0 के बराबर हो गया, ये फिर कौन को रिप्रेजेंट ना करके क्या करेगा? पेयर ऑफ प्लेन्स को रिप्रेजेंट कर देता है हमारा। तो ये बरसते कि 0 एकदम ये कहे तो कुल मिला के हमारा क्या है? 2D में जो पेयर ऑफ स्ट्रेट लाइंस पढ़े थे, 2D में जो पढ़े थे क्या? पेयर ऑफ स्ट्रेट लाइंस पढ़े, वहां पढ़ते।
I don't know. Someone is talking something.
I think somebody is teaching someone. So that's the issue.
Yes. Yeah. Okay.
Actually, that is Bihar language, sir. There's a problem. We cannot translate proper Hindi.
Yeah. Okay.
Hello.
Respected
Hello,
sir.
sir.
Very good
Hello.
afternoon, sir.
Yeah. Yeah. Tell me.
Sir, can I use regression analysis with secondary data?
Yeah. Secondary data you can use it. With the primary data also you can use. Primary data means not the questionnaire data. It should be quantitative data, not qualitative. If it is qualitative and quantitative, go for logistic.
Sir, I have a data of international trade of India and Russia. And a lot of data we have taken. Then for dependent and independent variable, sir, how we have to clarify my dependent and independent?
You can you see I cannot. I mean you can take my this. I do a lot of data analytics. So what you do is that here you can share that. I will do the analysis and then send it through email. My email ID I have already given in my this thing. You can see that and then send it the data. I can as well do that here, definitely. Without I don't charge anything. Free it is. It's my passion of doing data analytics. That's it. I'm doing it for the past 40 years, 45 years.
So for Likert scale, we have to do the logistic.
Sir, please
combination of qualitative and quantitative, then it is logistic.
Good afternoon, sir. Sir, my question is, my name is Sandra from Bitsville, Goa. I wanted to ask one question because you mentioned that we can do one logistic regression with one qualitative variable.
Not one, many also. Many also.
That was my question. So that.
Multiple MLR, it is called multiple logistic regression.
Okay, sir. Thank you. That was my question actually, whether we can do for more than one. Thank you so much.
No, you can do.
Thank you so much, sir.
I told you now 0, 1 is 1, or 1, 2 is 1, 1, 2, 3 also. You can go up to n.
Thank you, sir. Thank you, sir, for that. Thank you very much.
And for all the qualitative data, sir?
All the qualitative data, I mean, no. Only for some few qualitative data, you can as well do the this regression, dummy regression. I told you, I've given one example. Degree, yes, no. You can as well go for that.
Sir, please share your email ID in chat box, sir. Please, email ID, sir, आपकी.
ठीक है, अभी भेज दो.
Good afternoon, sir. My question is, what will be better to take for interpretation, like unstandardized beta coefficient or standardized beta coefficient? Which will be better for interpretation?
No, everything you have to interpret. Beta naught, beta 1, beta 2, everything you have to interpret.
No, sir, there is a unstandardized beta and standardized coefficient beta. So, sir, we will interpret two or only for standard.
No. Unstandardized only you have to take it.
Okay, sir. Thank you, sir.
Right. I've given it my Hargopal vajjha@gmail.com. Okay. Madam, is it 11:30 or 12 it is my lecture?
It's fine,
11:30, sir.
11:30, yeah, that's right. Yeah.
Madam, can you please share the feedback link?
So you'll have to wait for some more time. Are the questions over from the participants?
Yes, ma'am. Madam, yesterday I attended full lecture.
Sir, we will discuss about those things later on, sir. Could you please pardon us?
Oh, okay, okay.
Jyoti?
Okay, ma'am. On behalf of the Department of Business Management, it's my privilege to propose vote of thanks. I would like to express my deep gratitude to Professor Haragopal sir for such a wonderful and informative session. Thank you, sir, for your detailed explanation on T-test for simple regression, F-test for multiple regression with live examples. Sir has given valuable inputs on multiple regression models, stepwise regression with case studies, and how to remove potential explanatory variables in succession and testing for statistical significance after each iteration. Sir, we are really enlightened with your knowledge and presence, sir. So once again, I thank all the participants for their active participation.
Very good number. First time I'm seeing it. So many people. Really, you have really worked hard. Thank you. Thank you.
Thank you so much, sir.
So
Thank you
400
so much.
participants you have. Really great. It's great.
Sir, actually, the registrations are much more than that, sir. The registrations are almost 1,100 and something. But because the capacity is only 500, so we are accommodating only to that extent. The remaining we are
Yeah, Sudarshan Reddy
live
is very
streaming on
effective.
YouTube, sir.
My colleague in Usmania, Sudarshan Reddy, your secretary, is
Yes, sir.
really working hard. Nice guy, right?
Thank you so much, sir.
You just pass on my remembrance to him.
Sure,
Hargopal.
sir. Sure, sir.
Thank you. Thank you. I'm dropping off.
Thank you so much, sir. Thank you so much.
Thank you.
Thank you very much, sir.
Petition feedback, please. all the participants who have submitted your feedback form can leave the meeting.